Namaskaram. In this session, we will discuss one of the most useful concepts in linear algebra, that is projection. It is used in method of least square, principal compound analysis, and machine learning. The solution of last formula. Okay, before discussing the projection on an arbitrary interval space, we analyze the concept of projection in two-dimensional geometry. Then we will extend those concepts in higher dimensional spaces. Okay, in 2D, this is our vector x and this is vector A. We know that all the vectors are starting from origin in 2D or 3D. So, what is the projection means? The projection means the perpendicular projection. Okay, you think about this perpendicular line segment. Then this point is a projection of x. So, we consider the vector like this. You think about a vector like this. This is the projection of x in the direction of a. Okay, our aim is to find this vector. We denote this vector by u. Then what about this vector? What about this vector means? We know all the vectors are starting from origin. So you think about a vector like this, parallel to this one, and the same size. Okay, let it be v. Then my question, what about u plus v? By vector addition, how to add two vectors? You translate this vector at the tip of u, then you consider this line segment, then this is the vector u plus v. Okay, if you denote this is v, then this vector x is nothing, u plus v. Okay, so our aim is to find two vectors u and v such a way that u plus v equal to x and u is the projection vector. Okay, how to find u and v in 2D? Okay, it is clear that u is parallel to a. So we can choose u as some lambda a. That is a property of vectors in 2D. So since u and a are parallel, so one of them is a scalar multiple of other. Since u equal to lambda a, then what about v? We have a relation like this, u plus v equal to x. So what is v? V equal to x minus u. What is u? U is lambda a. That's why u equal to lambda a and v is equal to x minus lambda a. Okay. Then we have what from this geometry it is clear that u and v are perpendicular. U and v are perpendicular means in two-dimensional vector calculus that means u dot v equal to 0. And what is u dot v? Okay, if you choose u as u1 u2 and v as v1 v2, then u dot v is equal to u1 v1 plus u2 v2. In terms of Euclidean inner product, suppose you visualize these two vectors are members of R2. Okay, then with respect to Euclidean inner product, it is clear that this is nothing our inner product of UV. Okay, so instead of u dot v, I am going to write inner product of UV. This is Euclidean inner product. So this become inner product of UV equal to 0. Okay, so this implies what? This implies inner product of what is U? U is lambda a and what is V? X minus lambda a equal to 0. Then using the distributive property of inner product, you can expand this as inner product of lambda a x plus lambda a minus lambda a equal to 0. Using the property of inner product, you can take this lambda outside because lambda is a scalar. So lambda into this one plus here one lambda and minus lambda. So this becomes minus of lambda square a equal to 0. Again one lambda is common, you can take outside. So this becomes lambda into inner product of ax minus lambda into inner product of a equal to 0. We know that product of two numbers, suppose some c into d equal to 0. Suppose they are numbers. Then this implies either c equal to 0 or d equal to 0. Okay. Similar to this, here lambda is a number and this term inside this bracket also number. The product of two numbers equal to 0 means either lambda equal to 0 or the second time is 0. Okay. So here my claim is this condition is always true. Why? Suppose this is true, lambda equal to 0. Lambda equal to 0 means what about u? If lambda equal to 0, then what about u? U equal to 0. And what about v? When lambda equal to 0, v equal to x. Then what is the meaning? V equal to x. V equal to x means x is in this direction. That means they are perpendicular. Okay, so u and v are perpendicular. This means that is our x and a are u and v are perpendicular means now v equal to x, so x and a are perpendicular, so x is perpendicular to a, x is orthogonal to a, x is orthogonal to a means inner product of ax is equal to 0, so lambda equal to 0 implies inner product of ax equal to 0. Then what about this term? In this term now this is 0 and lambda is already 0, so entire time is 0. So whatever be the case, this condition is always true. Inner product of ax minus lambda into inner product of a equal to 0. Okay. Okay, so this implies inner product of ax minus lambda inner product of aa equal to 0. This is always true. So we are starting from inner product of uv equal to 0. If inner product of u and v equal to 0 implies this is always true. So our aim is to find this unknown lambda. Okay, this a is known, x is known. So to find u and v, the only unknown is lambda. Now you can solve lambda from this equation. So what is lambda? Yes, lambda is equal to inner product of ax by inner product of aa. Okay, so then you can write u and v. Just substitute lambda in these two equations. So u and v are, so u equal to inner product of ax by norm. Yeah, this is actually norm a square, right? Norm a square into a, and this is actually norm a square. That's why like this. And v is equal to x minus, instead of lambda, inner product of ax by norm a square into a. Okay, and the vector u is called projection of x onto a, and v is called orthogonal complement. Okay. Okay, suppose instead of x, suppose our x is like this. Then how to find the projection, or what is the projection? Projection is always the perpendicular projection. Okay, so for finding the projection, you have to extend this vector in this direction and you take the projection 90 degree. So this vector is the projection of this vector in this direction, in the direction of A. Okay, we consider problem. Find the point on the line x plus 4y equal to 0 closest to the point minus 1, minus 3, minus 1. So first you have to analyze the geometry of this problem. Okay, this is the geometry of this problem. First you identify the point minus 3, minus 1. And to find the straight line x plus, to draw the straight line x plus 4y equal to 0, we find 2 points. When x equal to 0, y also 0. When y equal to 1, x equal to minus 4. Then you identify, then locate the points, then you can't be the straight line. Okay, anyway we have to find the closest point in this straight line from this point. So closest point means you have to identify the perpendicular one. Clear? And this is the closest point. Okay, and we know that with respect to the term projection, we have to find, suppose you know this vector means this vector, and then this is the point closest to this one in this straight line. So that is a projection of which vector? Yes, it is the projection of this vector. So we can take it as x, projection of x in the direction of A. So we have to choose a vector A. Our aim is to find the closest point in the straight line. So we have to choose a vector in this direction or a vector from the straight line. That is very easy because already we know a point from the straight line, minus 4, 1. So we can choose our vector A as minus 4, oh, sorry, minus 4, 1. Minus 4, 1. And what about x? X is equal to minus 3, minus 1. Okay, our aim is to find the closest point means this point that is given by our u projection. So we have to find u. What is the formula of u? Yes, u is equal to inner product of ax by norm a square into a. So first we have to find inner product of ax. So what is the inner product between a and x? A is given, x is given. So we have to find the Euclidean inner product. That is minus 4 into minus 3 plus 1 into minus 1, that is 11. Okay, next we have to find norm a square. How to find norm a square? That's the inner product of AA. So inner product of AA means minus 4 square, minus 4 square plus 1 square, that is 16 square plus 1, that is 17. So u equal to 11 by 17 into the vector A. Vector A is minus 4, 1. So this become minus 44 by 17 comma 11 by 17. So this is the vector, this is the vector u. Okay, that means the coordinate of this point is this one. Okay, yes, answer is, so this is the closest point in the straight line to the point minus 3 minus 1. Okay, next we are going to define the general projection, the projection in a general space. Let V be any finite dimensional inner product space for a non-zero vector x element of V and a reference vector a element of V. We define the projection of x onto A as, and we denoted by projection, read as projection of x in the direction of A. Okay, write like this, equal to, we extend the concept in 2D similar to in higher dimension, inner product of ax by norm a square into A. Okay, in 2D this is our u, and we have one more vector v. What is vector v? That is v is equal to x minus u. In 2D we know that this u and v are perpendicular in our normal sense. Now we consider general space. Okay, so in this general space also there is a nice property between u and v. They are orthogonal with respect to the inner product. Okay, that's our next problem. Show that projection of x a to a and x minus u. X minus u means x minus the projection are orthogonal. That means you have to show that their inner product equal to 0. Okay, to show that they are orthogonal, we have to show that, this stands for, we have to show that inner product of projection of xa and x minus projection of x is 0. Okay, this means we have to show that. Okay, then instead of this equation, I am going to show that inner product of a comma x minus projection of x equal to 0. Why? We know that the projection is lies in the direction of a, right? For example, you consider our 2D case. Here, this is our vector a, this is our x. Then what about the projection? Projection is this one. So direction of projection and direction of a are same. Okay, so instead of evaluating this inner product, I am going to evaluate the inner product between a and this one. If this is 0, if this is true, then this is also true. Okay, so next we consider this side. Okay, so this become inner product of a comma x minus, instead of projection I am going to write inner product of ax by norm a square into a. Next we expand this inner product using the property of inner product, so this become our distributive property. This is like this, and again this x, and now we know that this quantity is like a lambda, the scalar, so you can take outside. So this become minus inner product ax by norm a square into inner product of a. And what about inner product of a? Yes, we know that they are same. This is same as our norm a square, so you can cancel it. Now this become inner product of ax minus inner product of ax, so that is equal to 0. So it is clear that a and x minus projection are orthogonal. They are orthogonal means these two are orthogonal because projection and a are the same direction. So projection of x and x minus projection of x are orthogonal, similar to our two-dimensional geometry. Here we consider the general space, general inner product space. Okay, so we are going to define this as orthogonal complement, like our V in 2D. Okay, so yes, x minus projection of x is called orthogonal complement of x. Okay, consider a problem. When the projection and orthogonal complement of x is equal to 2t square plus 3t plus 1 onto a equal to 5t square plus 6 in p square. Okay, here we consider the vector space p square, inner product is p square. So we have only one, now we know only one inner product on p square, that is the induced inner product. Okay, Euclidean inner product induced in p square, the inner product induced by Euclidean inner product. Okay, so we will solve this problem using induced inner product, okay, with respect to the standard basis. If the inner product is different, if they specify a particular inner product, then we will use that inner product. Okay. Okay, we know that the projection of x in the direction of a is equal to inner product of ax by inner product of a or norm a square into a. Okay, so we have to compute these two inner products. Okay, what is the inner product of a and x? Using our induced inner product with respect to standard basis. Yes, we know, first of all we have to find the coordinate of a. Coordinate of a and coordinate of x, then take the Euclidean inner product. What is the coordinate of a? Coordinate of a with respect to standard basis, that is 5 0 6, right? And similarly, what is the coordinate of x with respect to standard basis? That is 2 3 4. Then we consider the Euclidean product. So what is ax? That is 5 into 2 plus 0 into 3 plus 6 into 4, right? This is equal to 34. Similarly, you can find inner product aa, that is equal to 5 square plus 0 square plus x square, that is 61. Okay, now you can evaluate this projection. So this is equal to 34 by 61 into a. What do you say? A is equal to 5t square plus 6. So if you expand this bracket, this become 170 by 61 t square plus 204 by 61. Okay, so this is our projection. That is our u. Okay, next you have to find the orthogonal complement. How to find the orthogonal complement? Yes, that is x minus u. Okay, so x is here, so you simply consider to find the orthogonal complement, that is equal to this vector minus u means this projection. Okay, yes, so the orthogonal complement is equal to vector x is this one minus projection is this one. Okay, then on simplification this is like this. U means our projection, that is this one, and orthogonal complement is like this: 6 minus 68 by 61 t square plus 3t plus 40 by 60. Okay, okay, this is your homework. Thank you.